Hi, I'm Sean.
And I'm Jordan, and for our final project, we decided to design and draw guitars.
We call it SJ Guitar, and this is how we did it. The list of equipment used in this project is extensive, starting with an Allen-Bradley ControlLogix L71 controller as the heart of the process, that is bridged with an EMTY Ethernet IP module so we can communicate with devices over Ethernet, such as an Allen-Bradley PanelView 1000 Plus terminal as a human-machine interface. We also used a DeviceNET module and Data Highway Plus Remote I/O combo card. The DNet module was used to control the barcode scanner for Auto ID mode. The RIO section of the combo card connects to our flex rack, communicating with conveyors, pneumatic control systems, and robot I/O.
We also use a Fanuc M6IB robotic arm. We have the robot set up for both Ethernet and RIO communication. We're using digital and group I/O points to send and receive data back and forth between the ControlLogix and the robot. The teach pendant was used to program and teach positions to the robot. The entrance conveyor VFD is being controlled through 3 different programming methods. We have 6-speed digital, Ethernet, and analog speed control methods. This is our custom shop guitar screen, so the operator has the ability to choose which kind of components they want on their guitar. Once they have their selections made, they can click the load FIFO button and then it goes to the FIFO screen.
The FIFO display screen shows the numeric values of each guitar and is read by the CLX controller. The order display screen translates the numeric values from the FIFO into messages that the operator can understand. As you can see, we currently have 4 orders in the FIFO stack. Once orders are placed, then we will start the sequencer in push button indexing mode. This means you must press the advanced push button each time you want to progress the sequencer step. Once the pallet triggers the photo eye, the first order in the stack gets unloaded into the current order, also known as the FIFO output. Once the lift locate unit rises with a pallet present, this will send a signal to the robot to start the drawing via robot digital inputs.
The robot pulls data from various DT files to create its drawings. These files start at a top position on the corner of the page. The robot program then reads the XYZ positional data to tell the robot which point to move to next. DT files were used extensively in our project. Each component of the guitar is its own separate DT file.
To start, we took high-quality images from Google and imported them into Illustrator and traced the images. From that point, we exported them into a .dwg file and put them into AutoCAD.
Once the drawings were in AutoCAD, we made measurements from our top corner position to the beginning of the component of the guitar that we wanted to draw. We also had to plot out each point on the component that we wanted the robot to move to next. After we had all this data, we put it into Excel to create our DT file. In Excel, we had columns for XYZ positional data. These columns would tell the robot to move in linear motion. In our other 3 columns in Excel, we had XX, YY, and ZZ columns. If we had data in this column, then it would tell the robot to move in circular motion. After we had our DT files created in Excel, we had to export them as a .prn file. We would open the .prn file in Notepad++, and once that was open, we would save it as a .dt file. The DT files were then moved into the robot controller. Through our Carol program, this would select the DT file that it's going to draw. As you can see, the robot is drawing a stock red Gibson guitar that was selected earlier on in the video. The main idea of our project is to make stock production guitars, or to give you the option to customize your guitar with all your favorite components. The next guitar we're going to be drawing is a blue PRS Custom 24 stock guitar. On the right side of the screen we have a preview of the selected guitar that we want to draw.
The next sequencer mode of operation is event-driven mode. This means that from photo eyes and proximity sensors across the conveyor system, the system will make decisions of how the sequencer will now step. Once the pallet touches the photo eye, again, the order will now go into the FIFO output. We use 2 programming methods to control the robot. One's called Teach Pendant and the other is called Carol. We made a main program running off Teach Pendant, and from there we called separate Carol files containing routines and select case ofs for decisions made by the robot. Within Carol, we taught a total of 9 positions for the robot to read. And from that point, so Teach Pendant could also read those positions, we had to use 9 position registers within Carol. At the top of the Carol programs, we had to declare position registers 1 to 9 as XYZ WPR positions. From there, in the read data routine, we had to make each position register equal a position that we had previously taught. Once the position register has held the positional data that we had taught, then both Carol and Teach Pendant can utilize that data as we command it to. For drawing complex DT files like each neck on the guitar, including inlays, we had to cut down the cycle time of each drawing of the guitar to under 3 minutes. We did this by going into each DT file and making every move away, move near, and move to command to a different speed. Doing this means going into a 350-line DT file, finding each line and writing the commands if count equals line X, line Y for as many lines as necessary. Then using the Carol syntax $speed, we make the speed equal a specified value.
Here's an example of drawing a blue stock production Fender Telecaster using a barcode scan. This is an example of a red PRS Custom 22 neck with a Gibson body. This is also known as a PRS single cut guitar.
Thanks for watching our video for our Auto 2100 Capstone project as part of the Electromechanical Engineering Technology program at Durham College.
This is SJ Guitars. Hope you enjoyed it.